Okay, we are back to do an example of a linear programming problem. This is a non-contextual problem, meaning it's not a story problem. It doesn't have a real world context. It's just a plain old problem out of a textbook or whatever. Here's our system of constraints. And this is our objective function. So what we're going to be doing is we're going to be finding the maximum and minimum value of our objective function subject to this system of constraints. So the first thing we need to do is get our system of constraints graphed so that we can identify the feasible region and find the vertices of the feasible region. So let's look at this system. The first two here together, you're going to see that a lot. So we might want to kind of take note of what that means. These two constraints, when they're put together, if you think about the xy axis, x equals 0 is a vertical line that goes through 0. So that's basically the y-axis. And if you're looking at greater than or equal to 0, that's going to shade to the right. Y is greater than or equal to 0 is a horizontal line through 0, so that's the x-axis basically. And being greater than 0 means we're shading above. So when you put those two constraints together, basically what you're doing is you're shading this first quadrant. So whenever you see these two constraints together, that means that you will only graph in quadrant 1. So these two constraints together mean you will only graph in quadrant 1. So often when I see those, I go ahead and make my coordinate plane just smaller like this, so that I really only have quadrant 1. So let's move on, because we know we can pretty much ignore these first two constraints because they just mean use only quadrant 1. So I'm going to go on to x is less than or equal to 5. And x is less than or equal to 5 is going to be a vertical line. It's going to go through x equals 5, and we're going to be shading to the left, and it will also be a solid line. So here's my quadrant 1. I've got it marked off 1, 2, 3, 4, 5, and I will be drawing a vertical line through x equals 5. Hopefully it'll be a pretty good vertical line here. Well, it's not awesome, but I've seen worse. And we're going to be shading to the left. Now keep in mind, I don't want to start shading all over my graph because I'm really only going to color in the overlapping region. So we'll get that on. We'll go on to the second constraint here, and that is in standard form. So I will use the cover-up method to figure out the x and y intercepts. So I'll cover up the y, and that gives me x equals 7, so that will be 7, 0. And then I'll cover up the x, and that gives me y equals 7, so 0, 7. Again, I have a solid line, so I'll put 7, 0, 1, 2, 3, 4, 5, 6, 7, 7, 0, and 0, 7, 1, 2, 3, 4, 5, 6, 7. And then I'm going to connect those dots using a solid line. I want to use a test point to see which side of that line to shade. So let's test 0, 0 since it's not on the line. So I get 0 plus 0 is less than or equal to 7, which is true. So this one will be shaded below. And we're on to the next constraint, which is also in standard form. So I'll cover up again. So I get x equals 4 when I cover up the y. So that's 4, 0. Cover up the x. That gives me 2y equals 4. Divide by 2 gives me 0, 2. So I have 4, 0 and 0, 2. This is a solid line as well. We'll graph that. And test 0, 0 gives me 0 plus 0 is greater than or equal to 4, which is false. So I'll be shading away from the origin, so that will be above the green line here. And the last constraint, I'll use cover-up method again. So cover up the y, I get x equals -5. So -5, 0. Cover up x, negative y equals -5, so that will be 0, 5. Well, I hope I have enough room to count -5. So let's see. 1, 2, 3, 4, 5. We'll just make do. Pretend that's -5 over there. And 0, 5. 1, 2, 3, 4, 5. And connect those dots right through the hole in the paper. That's all right. And test 0, 0. So we have 0 minus 0 is greater than or equal to -5, which is true. So I'm going to shade this one towards my test point, so below the purple line. Now when you shade your feasible region, make sure you remember that you're only working in quadrant 1. So I'm automatically restricted to this section here. When I look at where to shade. So I'm going to pay attention to my arrows. I'm going to be above the green line, below the purple line, below the orange line, and to the left of the red line. So it looks like it's going to be this region in here. So this is what we call, do you remember what we called that? That is called the feasible region. And then the next step, remember in linear programming, is going to be to find the vertices of that feasible region. Now some of them, we're in luck, are very easy to just tell by looking. Like this one right here was already one of our y-intercepts up here. So this ordered pair, this vertex, can automatically be labeled 0, 2. Similarly, this vertex was from the purple line, and it was at 0, 5. 0, 5. And this one was the x-intercept of the green line, so 4, 0. And this one right here goes with that vertical line, so it is 5, 0. This one is not a vertex because it's not attached to the shaded region. So I really only want 1, 2, 3, 4. I've got one here, 5, and one here, 6. So I don't have to worry about any other intersections. Now these two are the only ones that I'm actually going to have to set up systems of equations to find. So let's go ahead and get that started. This one right here is the intersection of my purple line, which was x minus y equals -5. So it was purple and orange. Orange was x plus y equals 7. So when I solve that system, it looks like elimination will work really well. So the y's will drop out. So when I add those together, I get 2x equals -5 plus 7 is 2. So x equals 1. and then sub that back into one of these. So I have 1 plus y equals 7, so y is 6. So that's going to give me the ordered pair 1, 6. So I'll label that on here, 1, 6. And then I'm going to have to do a similar situation for the other intersection. And this one is the intersection of my red line and my orange line. So the red line was x equals 5, and the orange line was x plus y equals 7. I'll solve this one by substitution, so I'll substitute 5 in for x, so 5 plus y equals 7, gives me y equals 2. So the ordered pair will be 5, 2. We'll label that on our picture, 5, 2. After we've found all the vertices of our feasible region, what we're going to do is substitute each one of them into the objective function and figure out which one gives me the maximum and the minimum value. So my objective function was f of x comma y equals negative 0.4x plus 3.2y. So I'm going to have to plug in each ordered pair from the vertices. So f of 0, 2, f of 0, 5, f of 1, 6, f of 5, 2, f of 5, 0, and f of 4, 0. So we have 7 different ones to test out. Is that 7? 1, 2, 3, 4, 5. Excuse me. We have 6 different ones to test out. So we're going to substitute in. So we'll do negative 0.4 times 0 plus 3.2 times 2. So that negative 0.4 times 0 is 0. So that goes away, and that equals 6.4. And then we'll do negative 0.4 times 0 plus 3.2 times 5. So again, that part drops out, and that's going to equal 16. And then negative 0.4 times 1 plus 3.2 times 6. That is negative 0.4 plus 19.2, which is going to be 18.8. And then negative 0.4 times 5 plus 3.2 times 2. So that is negative 2 plus 6.4, which will be 4.4. And then negative 0.4 times 5 plus 3.2 times 0. That drops to 0, and we get negative 2. And then negative 0.4 times 4 plus 3.2 times 0. That drops to 0, and we get negative 1.6. So now we have to identify the maximum and minimum. So the biggest value is 18.8, and the lowest value is negative 2, which we will state kind of as a sentence. So we'll say the maximum value is 18.8, and it occurs when x is 1 and y is 6, which we got from that information. Then we want to state the minimum value is negative 2, and those are the conditions under which it occurs. So we'll say the minimum value is negative 2, and it occurs when x is 5 and y is 0.